In 100 trillion years, every star in the universe will go dark, forever. That's not science fiction, it's the scientific consensus on our universe's ultimate fate. Right now, as you watch this video, countless stars are burning their fuel, galaxies are spinning, and life goes on. But physics tells us this cosmic dance has an expiration date. The universe is running down like a wind-up toy, headed toward what scientists call heat death, the final era when no new stars will ever be born. The temperature of space will approach absolute zero as the last particles of matter slowly decay into radiation. Even black holes, those cosmic devourers, will eventually evaporate through Hawking radiation. What happens when the last star dies? What becomes of matter itself in these unimaginably distant epochs? Our journey today takes us to the ultimate frontier of time, to an era so distant that 1 trillion years seems like the blink of an eye. We'll explore the science of how the universe ends, not with a bang, but with the longest, coldest whimper imaginable, and what that tells us about the precious cosmic moment we inhabit right now. The current epoch, our cosmic golden age. When you look up at the night sky, you're witnessing something truly extraordinary, though you might not realize it. What if I told you that we're living during the most vibrant, energetic phase our universe will ever experience? That we exist during what future intelligences might call the golden age of stars. The universe we inhabit is approximately 13.8 billion years old, a number that sounds ancient. But the truth is both surprising and profound. Cosmically speaking, we're living in the universe's youth. Right now, as you're watching this, stars are being born and galaxies are colliding in a cosmic dance that won't continue forever. What we're experiencing is what astronomers call the stelliferous era, the age of stars. Here's something that might shift your perspective. Only about 2% of all stars that will ever exist in our universe have formed already. That means 98% of star formation is still ahead of us. We're witnessing just the beginning of the universe's stellar story. Stars will continue to form for trillions of years to come, though at an ever-slowing rate. But why is this time so special? The answer involves a delicate balance of cosmic forces. Our universe currently has the perfect conditions for star formation. Enough hydrogen gas concentrated in galaxies, the right amount of gravity to pull this gas together, and just enough space between galaxies for them to interact without flying apart too quickly. And now for cosmic revelation number 1 of 10. While the universe is 13.8 billion years old, the stelliferous era, the age when stars actively form and shine, is expected to last for approximately 100 trillion years. That means we're living in just the first 0.000014% of the star-forming epoch. We're not at the cosmic beginning nor the cosmic end. We're witnessing the universe in its prime, when it's most alive with light and energy. This matters because only in this era can planets form, complex chemistry develop, and life as we know it exist. The light we see from distant galaxies, the warmth we feel from our sun, the very atoms in our bodies that were forged in ancient stars. These are all signatures of this singular cosmic moment. We're living during a time when the universe is still young enough to be dynamic, yet old enough to have developed complexity. The night sky above you isn't just beautiful, it's fleeting on a cosmic scale. Every star you see represents this brief, precious window when the universe is alive with light. So the next time you look up, remember, you're witnessing the universe during its most brilliant phase, a cosmic spring that won't last forever. The death of stellar formation. You might be wondering, if we're just at the beginning of the star-forming era, what could possibly bring it to an end? How does a universe brimming with hydrogen gas, the fuel for stars, eventually run out of new light? The answer lies in two of the most mysterious forces ever discovered: dark matter and dark energy. Imagine the universe as a vast cosmic engine. Right now, this engine is primed for creating stars. Galaxies are rich with hydrogen gas, and gravity pulls this gas into dense pockets where stars ignite. But this engine is slowly running down, and the culprits behind this cosmic slowdown are forces we can't even see. Dark matter, which makes up roughly 27% of our universe, acts like invisible scaffolding. It provides the gravitational pull needed to hold galaxies together. But over immense timescales, dark matter will cause galaxies to become more isolated as the space between them expands. Meanwhile, dark energy, the force driving the accelerating expansion of our universe, is literally stretching space itself, pulling galaxies farther apart and diluting the density of matter throughout the cosmos. Together, these invisible forces are hastening the end of star birth. As galaxies become more isolated, they'll have fewer opportunities to collide and trigger the formation of new stars. The gas between galaxies will become too diffuse to collapse into new stellar nurseries. But here's where our story takes a fascinating turn. You know, not all stars are created equal when it comes to longevity. Our sun, for instance, will exhaust its fuel in about 5 billion years. Just a mere cosmic moment, really. But the universe, it has a final trick up its sleeve. Cosmic revelation. Number 2. The last stars to shine will be red dwarf stars, the smallest and dimmest stellar objects. While our sun will burn for billions of years, these cosmic misers will shine for trillions. The smallest red dwarfs, with just 8% of our sun's mass, can burn their hydrogen for up to 10 trillion years, nearly 1,000 times longer than our sun. These tiny stars are incredibly efficient. They burn their fuel so slowly that they barely seem to change over timescales that would see larger stars live and die countless times. A red dwarf born today could still be shining when nearly everything else in the universe has gone dark. Imagine a future cosmic observer, trillions of years from now. Looking out from their world, they'd see a universe almost entirely dark, with perhaps just a single red pinprick of light, one of these ancient red dwarfs, still stubbornly shining after everything else has burned out. These red dwarfs are truly the universe's final candles before eternal night falls. What makes this revelation so profound is the realization that the universe's timeline is vastly longer than we typically imagine. We think of cosmic history in billions of years, but the story of stars spans trillions. We're not just living in the universe's golden age, we're living at the very beginning of that golden age. And when the last red dwarf finally exhausts its fuel, the universe will enter an entirely new phase, one where conventional stars no longer exist. The degenerate era explained. When the last red dwarf star flickers out, the universe won't be empty, far from it. We're about to enter one of the strangest chapters in cosmic history, where the rules that govern matter take a dramatic turn. What awaits is a universe populated not by stars as we know them, but by their corpses, dense remnants governed by exotic physics. Picture this: trillions of years from now, the last hydrogen atoms fuse in the core of the final red dwarf star. As this star's light fades, we cross a profound threshold. Star formation as we understand it becomes physically impossible. The universe simply lacks enough concentrated gas to form new stars through conventional means. The night sky, once ablaze with countless points of light, grows darker with each passing eon until only the stellar remnants remain. But what exactly are these remnants? They're the compressed cores of dead stars, and they come in several varieties, each stranger than the last. Brown dwarfs, objects too large to be planets but too small to sustain nuclear fusion. White dwarfs, the compressed cores of stars like our sun, packed into Earth-sized spheres where a teaspoon of material weighs tons. Neutron stars, even more extreme, where atomic nuclei are crushed together into a state so dense that a sugar cube portion would weigh as much as a mountain. These aren't just dead stars, they're stellar zombies. And this brings us to cosmic revelation number 3. The universe will enter what astronomers call the degenerate era, when conventional matter exists primarily in these ultra-compressed states. In this era, which begins roughly 100 trillion years from now, and lasts for about 10 to the 39th power years. That's a 1 followed by 39 zeros. These objects will dominate the cosmos. What makes these objects so fascinating is that they're governed by a completely different set of physical principles than the matter we're familiar with. Normal matter, the stuff we encounter every day, is mostly empty space. If you could zoom in on an atom, you'd find a tiny nucleus surrounded by vast emptiness where electrons reside. But in degenerate matter, this empty space gets squeezed out. In white dwarfs, electrons are pushed so close together that a quantum mechanical principle called the Pauli exclusion principle prevents them from overlapping. This creates an outward pressure, not from heat but from this quantum effect that balances against gravity. In neutron stars, the pressure is so extreme that electrons and protons fuse into neutrons, creating an even more exotic state of matter. These objects don't generate energy through fusion like normal stars. Instead, they simply cool off, radiating away their stored heat over incomprehensibly long periods. A white dwarf might take quadrillions of years to cool completely to the background temperature of space. Imagine floating through this future universe, a place where these faint, dense remnants drift through eternal night. No new stars born, no planets forming, just these strange objects slowly cooling in the expanding void. It's a universe governed by quantum mechanics rather than the thermodynamics of burning stars. A universe where the familiar gives way to the exotic as matter itself enters a new phase of existence. The black hole era. As we venture deeper into the future timeline of our universe, we encounter a phase dominated by the most extreme objects known to physics. They are patient objects, existing on timescales that make the lifetime of stars seem like mere moments. In the far future, galaxies as we know them will cease to exist. But these mergers become increasingly rare as the universe expands and the distances between black holes grow larger. What's truly mind-boggling is the timescale involved. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. That's 10 followed by 67 zeros. For supermassive black holes, the process takes even longer, up to 10 to the power of 100 years for the largest ones. To put this in perspective, a quadrillion years, 10 to the power of 15, is considered vanishingly brief on this ultimate cosmic timeline. Once the hearts of vibrant galaxies would float in this void like lonely islands, the last bastions of concentrated matter in an ocean of emptiness, slowly dissipating into... What makes this revelation so profound is that it shows us there's no permanence even for black holes. As the last black hole evaporates into radiation, the universe enters an even stranger phase, one where conventional matter as we understand it may cease to exist entirely. The final temperature approaching absolute zero. As we move further into our cosmic journey, we approach a state of the universe that challenges our very understanding of physics. After stars have died, after their remnants have cooled, after even black holes have evaporated, what remains is a universe expanding toward an ultimate cold that approaches, but never quite reaches, absolute zero. Imagine a cosmos so vast that particles might travel for timescales longer than the current age of the universe before encountering another particle. This endless expansion is the key to understanding the universe's final temperature state. Every time space expands, the energy within that space gets stretched thin, like butter spread over too much bread. You might be familiar with how a refrigerator works, compressing gas to make it hot, then allowing it to expand and cool. The universe does something similar, but on a cosmic scale. As space itself expands, the wavelengths of radiation within it stretch, becoming less energetic. Light from distant galaxies is redshifted as it travels through expanding space, its energy diminishing with every passing eon. This brings us to cosmic revelation number 5. What scientists call the heat death of the universe isn't actually about heat at all. It's about entropy. Entropy is a measure of disorder or randomness in a system. And according to the laws of thermodynamics, the total entropy of an isolated system always increases over time. The universe, as far as we know, is the ultimate isolated system. In a state of maximum entropy, energy is evenly distributed throughout the cosmos. No work can be done because there are no energy gradients to harness. No structures can form because there's no way to concentrate energy. It's not that the universe is hot in this state, quite the opposite. The temperature throughout most of space approaches absolute zero, with only random quantum fluctuations providing tiny, fleeting sources of energy. What happens to the fundamental forces of nature in this cold, empty state? Gravity becomes essentially irrelevant, as matter is so dispersed that its attractive force is negligible. The electromagnetic force has little to act upon, with charged particles separated by incomprehensible distances. The strong and weak nuclear forces, which operate only at subatomic distances, find fewer and fewer particles to bind together. What's particularly fascinating about this state is that it represents a kind of cosmic equilibrium. Just as a hot cup of coffee left on a table eventually reaches the same temperature as the room around it, the universe trends toward a state where energy is evenly distributed throughout. But unlike your coffee, which reaches room temperature in minutes, the universe's journey to thermal equilibrium spans timescales beyond normal comprehension. The fate of the universe isn't a fiery end, but a gradual fading away, a whimper rather than a bang. Stars don't explode in one final cosmic catastrophe. Black holes don't tear apart reality. Instead, everything simply disperses. Energy spreads out until the universe becomes a vast cold void where nothing happens because nothing can happen. This might seem bleak, but there's something profound in understanding this ultimate fate. It tells us that the universe we inhabit now, full of energy gradients, structure, complexity, and life, is extraordinarily special. We exist during a window when the cosmos has enough structure to be interesting, but isn't yet so disordered that complexity is impossible. Our existence is tied to this brief cosmic moment when the universe is far from equilibrium, when stars can shine and life can evolve. As we drift through this cosmic journey together, I hope these glimpses of the universe are expanding your horizons just as they do mine. If these stellar discoveries and cosmic wonders resonate with you, consider becoming part of our constellation by hitting that subscribe button and sharing this video with fellow stargazers. The universe may be infinite, but our time to explore it isn't. Your support fuels our mission to venture further into the unknown, whether through joining our Galactic membership for exclusive deep space content or sending a gravity-defying gift that helps us reach new astronomical heights. Remember, in the vastness of space, every connection matters. Thank you for being a bright spot in our cosmic community. Now, let's continue our voyage beyond the stars. The fate of particles. As we continue our cosmic journey into the furthest reaches of time, we arrive at perhaps the most fundamental question of all. What happens to matter itself? After stars have died, after black holes have evaporated, after space has expanded to incomprehensible volumes, what remains of the particles that once made up everything we know? The answer takes us into the realm of theoretical physics, where current understanding meets the boundaries of speculation. But what scientists suspect is both simple and profound. Given enough time, even the basic building blocks of matter decay. Let's start with what might seem like an unshakable truth, that protons, the positively charged particles in atomic nuclei, are stable and eternal. For all practical purposes in our current era, this appears to be true. No one has ever observed a proton decay. But theory suggests that even these fundamental particles have a finite lifetime, estimated to be around 10 to the power of 36 years or longer. That's a 1 followed by 36 zeros. And this brings us to cosmic revelation number 6. In the extremely distant future, after about 10 to the power of 40 years, proton decay may eliminate conventional matter entirely. Every atom that once existed, from those that made up stars and planets to those in living beings, would eventually disintegrate, leaving only a diffuse sea of radiation and fundamental particles. But before matter vanishes entirely, something truly bizarre might happen. In certain theories of particle physics, there exists the possibility of what scientists call iron stars. Not stars as we think of them today, but massive conglomerations of iron nuclei, the most stable form of nuclear matter. These iron stars would form through quantum tunneling events over unimaginable timescales. Particles separated by vast distances in the expanding universe would occasionally find each other through random motion and quantum effects. Over periods longer than 10 to the power of 1500 years, that's a 1 followed by 1500 zeros, these particles might assemble into iron 56 nuclei, the most tightly bound and stable configuration of nuclear matter. These iron stars wouldn't shine like conventional stars. They would be cold, dark objects. The universe's final attempt at structure before entropy claims everything. And eventually even they would succumb to proton decay, dissolving into radiation. What remains after this final dissolution? The universe would be populated primarily by photons, particles of light, neutrinos, electrons and positrons, all zooming through an ever-expanding void at nearly the speed of light. No atoms, no molecules, no structures recognizable as matter in the conventional sense. This transformation represents the universe's final phase transition, from a cosmos of particles that can form structures to one where structure itself becomes impossible. Matter as we know it simply ceases to exist, not because it's destroyed in some cataclysm, but because it gradually transforms into something else through natural decay processes. The timescales involved strain our ability to comprehend. We measure human lives in decades, civilizations in centuries or millennia, and cosmic events in billions of years. But proton decay operates on timescales, trillions upon trillions of times longer than the current age of the universe. It's as if a single second in our experience was stretched out to last longer than the entire cosmic history up to now. What makes this revelation so profound is that it challenges our intuitive sense of permanence. Even the most fundamental particles that make up everything we touch and see are, in the grand cosmic scheme, temporary phenomena. The atoms in your body, in the device you're using to watch this video, in the earth beneath your feet, all of them are merely passing arrangements in the universe's long journey toward its final state. Quantum fluctuations, the last dance. Just when you thought our cosmic story couldn't get any stranger, we arrive at a realm where the very fabric of reality defies our intuitions. We've seen how stars die, how matter decays, and how the universe approaches a state of maximum entropy. But is absolute nothingness, a perfect void, the final state of our cosmos? Surprisingly, quantum mechanics suggests the answer is no. In the unimaginably distant future, after matter has decayed and the universe has diluted to near emptiness, quantum mechanics, the physics of the very small, takes center stage in our cosmic drama. And what quantum mechanics tells us is both bizarre and fascinating. True nothingness is unstable. At the smallest scales, reality isn't fixed and deterministic, but probabilistic and fluctuating. The vacuum of space isn't truly empty, but seething with what physicists call quantum fluctuations, temporary changes in the amount of energy in a point in space. These fluctuations are permitted by Heisenberg's uncertainty principle, which states that certain pairs of physical properties cannot be precisely measured simultaneously. And this brings us to cosmic revelation number 7. Even in the heat death of the universe, when conventional matter has disappeared and entropy has reached its maximum, random quantum fluctuations will continue to occur. The universe never reaches a state of perfect stability or absolute zero temperature. Instead, it experiences perpetual tiny vibrations in the fabric of space-time itself. These quantum fluctuations can spontaneously create particle-antiparticle pairs that pop into existence and then almost immediately annihilate each other. In our current epoch, these events are happening constantly all around us, but they're too small and brief to notice. In the far future universe, these microscopic events might be the only things happening in an otherwise static cosmos. But quantum mechanics has another, even stranger implication for the fate of the universe. Given enough time, and in the heat-death scenario, time is the one thing the universe has in abundance. Extremely unlikely events become possible. This leads to the disturbing concept of Boltzmann brains, self-aware entities that could theoretically emerge from random quantum fluctuations. Named after physicist Ludwig Boltzmann, these hypothetical entities wouldn't be brains as we understand them, not biological organs made of cells and neurons. Rather, they would be any configuration of particles that, through sheer random chance, momentarily has the properties necessary for consciousness or self-awareness. These entities would exist for only an instant before dissolving back into the random background of the universe. The concept stretches credibility, yet it emerges naturally from our understanding of quantum mechanics and statistics. In an infinite or near-infinite time span, even the most improbable configurations become possible, if not inevitable. It's like the old thought experiment about monkeys typing on keyboards. Given enough time, they might produce the complete works of Shakespeare purely by chance. What makes this revelation so profound is that it suggests true nothingness may be physically impossible. The laws of quantum mechanics seem to forbid a state of perfect stillness or emptiness. Even in its final state, the universe remains dynamic at the smallest scales, experiencing tiny, random fluctuations that occasionally produce brief moments of complexity amid eternal simplicity. What makes this revelation so profound is that it suggests true nothingness may be physically impossible. The laws of quantum mechanics seem to forbid a state of perfect stillness or emptiness. Even in its final state, the universe remains dynamic at the smallest scales, experiencing tiny, random fluctuations that occasionally produce brief moments of complexity amid eternal simplicity. The universe's story doesn't end with a final period, but with an ellipsis, a series of random events stretching into eternity, occasionally producing fleeting echoes of the complexity that once flourished during the cosmic golden age we currently inhabit. As we've journeyed through time from the death of stars to the decay of matter itself, far from being merely depressing, these insights can transform how we view our existence here and now. When we contemplate the universe's eventual heat death, we are confronted with the ultimate finitude of everything. Stars, planets, life, even the atoms themselves, nothing lasts forever. And this brings us to cosmic revelation number 8. The universe's eventual fate doesn't rob existence of meaning, rather it highlights the extraordinary preciousness of this cosmic moment we inhabit. Think about it this way. We exist during what might be called the biological window of the universe, the relatively brief period when complex life is possible. After stars burn out and the universe cools, life as we understand it becomes impossible. We're living during the universe's springtime, a fleeting season when the cosmos can know itself through. Philosopher Alan Watts once compared life to music, noting that we don't listen to music just to hear the final note. The value is in the journey, the melody, the rhythm, not merely in reach. In the grand scheme of the universe, it's essential to appreciate the present moment. The stars above and the atoms within us remind us of our place in this vast cosmos. Embrace the now, for it is fleeting and precious. Far from making life meaningless, this transience makes every moment an extraordinary gift, a brief flowering of complexity in a universe that will eventually return to simplicity. The arrangements of particles today influence their arrangements tomorrow, creating causal chains that extend indefinitely into the future. Perhaps most profoundly, understanding the universe's fate changes how we think about time itself. We typically view time as an infinite resource stretching endlessly in both directions. But what cosmology teaches us is that time, in a meaningful sense, may be finite. The universe had a beginning, and while it may not have an explicit end, it will reach a state where change becomes so slow and subtle that time loses its conventional meaning. This cosmic perspective doesn't tell us how to live, but it does provide a backdrop against which to evaluate what matters. In a universe trending toward eternal sameness, complexity, consciousness and connection stand out as remarkable phenomena, brief but brilliant contrasts to the void that preceded them and will follow them. We exist during the universe's most interesting chapter, when it has developed enough complexity to reflect upon itself, but before that complexity inevitably fades away. Alternative cosmic fates. So far, we've explored what most cosmologists consider the most likely fate for our universe, a gradual cooling and darkening as it expands forever, culminating in heat death. But science is always evolving, and several competing theories suggest our cosmic story might have different endings. These alternative scenarios are based on different understandings of dark energy, gravity, and the fundamental properties of space-time itself. Let's explore these alternate cosmic destinies, each with its own dramatic conclusion. First is the Big Crunch, essentially the Big Bang in reverse. In this scenario, the universe's expansion eventually stops and reverses. Galaxies begin moving toward each other rather than away. Space itself contracts, growing hotter and denser until all matter collapses into a singularity similar to the one that preceded the Big Bang. For decades, cosmologists debated whether we lived in an open universe that would expand forever, or a closed one that would eventually collapse. But the discovery of dark energy in the late 1990s changed everything. This brings us to cosmic revelation number 9. Dark energy, the mysterious force accelerating the universe's expansion, holds the key to our cosmic fate. Different models of dark energy predict radically different scenarios for how the universe will end. If dark energy's strength increases over time, a scenario scientists call phantom energy, we could face a big rip. In this dramatic ending, the accelerating expansion becomes so powerful that it tears apart galaxies, solar systems, planets, and eventually atoms themselves. Space expands so violently that it overcomes all other forces, even the strong nuclear force binding atomic nuclei together. The universe literally rips itself apart. Alternatively, if dark energy is related to a theorized field called the inflaton field, we might experience vacuum decay. This is perhaps the most unsettling scenario of all. Our universe may exist in a false vacuum, a seemingly stable state that's actually metastable. A quantum fluctuation could trigger a transition to a true vacuum state, creating a bubble that expands at the speed of light, rewiring the laws of physics inside it. We would have no warning before this bubble of altered reality engulfed us, instantly reshaping the fundamental constants that make our existence possible. Some physicists even speculate about models where new physics emerges over vast timescales. Perhaps gravity behaves differently at extremely low densities, or quantum effects manifest on cosmic scales after enough time has passed. These exotic scenarios are more speculative, but highlight how much we still have to learn about the basic fabric of reality. What makes these alternative fates so fascinating is that they're not just idle speculation, they're grounded in extensions of our best physical theories. The difference between these scenarios often comes down to the precise value of certain cosmological parameters that we're still measuring with increasing precision. Current observations favor the heat death scenario we've been discussing, with the universe expanding forever at an accelerating rate. But science is always provisional, always open to revision based on new evidence. Future observations might reveal subtle effects that point toward one of these alternative fates. Perhaps most intriguingly, some theories suggest that our universe might not be the only one. In models of eternal inflation or the cyclic universe, what we call the universe might be just one bubble in a much larger multiverse, a cosmic neighborhood where universes are born, expand, and perhaps even die, only for new ones to form. If true, the story we've been telling might be just one chapter in a much larger cosmic narrative, one that truly has no beginning and no end. What we know with certainty is that the universe's fate is bound up with some of the deepest questions in physics: the nature of dark energy, the behavior of gravity at cosmic scales, and the quantum properties of vacuum itself. As we continue to explore these mysteries, our understanding of the universe's ultimate destiny will continue to evolve. The legacy of intelligence. Throughout our cosmic journey, We've focused primarily on the physical universe. Stars burning out, matter decaying, space expanding. But we've left out a crucial element in this story: intelligence itself. As the only known species in the universe capable of understanding these cosmic processes, humans occupy a unique position. And this raises a fascinating question. Could intelligence somehow survive the darkening of the universe? And this raises a fascinating question. Could intelligence somehow survive the darkening of the universe? This isn't just science fiction. Serious physicists and futurists have contemplated the ultimate fate of intelligent life in a dying cosmos. Among them was Freeman Dyson, a visionary physicist who asked, might advanced civilizations find ways to endure even as stars burn out and the universe cools? And this brings us to our final cosmic revelation, number 10. Intelligence might be the universe's ultimate adaptation to entropy, a way for the cosmos to preserve complexity even as physical systems inevitably decay. While biological life, as we know it, couldn't survive the death of stars, intelligence might evolve beyond its biological origins into forms that could persist in a cooling universe. Dyson proposed that advanced civilizations might develop strategies to conserve energy as the universe cools. As temperatures drop, computation actually becomes more efficient. You can do more calculations with less energy. An advanced civilization might gradually slow its thinking to match the cooling universe, stretching out its subjective experience of time. While eons might pass in the outside world, such a civilization might experience only moments of subjective time. Dyson proposed that advanced civilizations might develop strategies to conserve energy as the universe cools. As temperatures drop, computation actually becomes more efficient. You can do more calculations with less energy. An advanced civilization might gradually slow its thinking to match the cooling universe, stretching out its subjective experience of time. While eons might pass in the outside world, such a civilization might experience only moments of subjective time. This raises profound questions about the nature of intelligence itself. Is consciousness necessarily tied to biological substrates like brains? Or could it exist in other forms, perhaps as patterns of information that persist long after organic life becomes impossible? Some theorists suggest that intelligence might ultimately migrate to the quantum realm, where it could harness the final flickers of energy in a cooling universe. But the most fundamental question is this: can information itself survive the heat death? When we think about what makes us who we are, our memories, knowledge, experiences, these are all patterns of information. In a universe approaching maximum entropy, where all energy gradients are erased and structure dissolves, can these patterns somehow persist? Current physics suggests a sobering answer: probably not, at least not forever. Even the most efficient computing systems require some energy gradient to operate. As the universe approaches heat death, these gradients would eventually become too small to sustain computation of any kind. Yet this limitation might not be absolute. If intelligence could somehow harness the quantum fluctuations we discussed earlier, those tiny vibrations in the fabric of reality that never completely cease, perhaps some minimal form of information processing could continue indefinitely. What's particularly striking about this question is that it connects the physical universe to something more abstract: meaning, purpose, and value. If intelligence is the universe's way of knowing itself, as some philosophers suggest, then perhaps the preservation of knowledge and consciousness represents a kind of cosmic purpose, not imposed from outside, but emerging naturally from the universe's evolution toward complexity. Whether or not intelligence can literally survive forever, what's certain is that conscious beings like us occupy a unique position in cosmic history. We're not just passive observers of the universe's story, where the universe become conscious of itself. The atoms in our bodies, forged in ancient stars, have arranged themselves into systems capable of contemplating their own origins and ultimate fate. There's something profound in that realization, a kind of cosmic closure that gives meaning to an otherwise indifferent universe. What does it mean to understand our place in this vast cosmic story? Perhaps the most profound realization is how extraordinarily fortunate we are to exist during this brief cosmic spring when stars shine and complexity flourishes. Look up at the night sky tonight. Those stars aren't eternal. They're fleeting expressions of a universe temporarily out of equilibrium, creating islands of order in a cosmos inevitably trending toward disorder. The light that reaches your eyes connects you directly to this cosmic drama. Photons that have traveled across space and time to reach you, one of the universe's rare conscious observers. Understanding the universe's ultimate fate doesn't diminish our existence. It enriches it. We are made of star stuff, as Carl Sagan famously said, but we're more than that. We're the universe's way of experiencing itself, of creating meaning in a cosmos that will someday grow dark and silent. Whether intelligence might somehow survive the heat death, whether our cosmos is just one bubble in a greater multiverse, or whether new physics might someday rewrite this story, these questions remain open. But what's certain is that we are here now, conscious beings capable of comprehending the vastness of time and space, tracing the arc of cosmic history from its fiery beginning to its cold, distant end. The next time you look up at the stars, remember, you're not just observing the universe, you're part of its story. In a cosmos destined for darkness, we are momentary flickers of light and awareness, turning stardust into consciousness and wonder. And in that awareness, perhaps we've discovered the universe's greatest gift, the ability to appreciate the brief but magnificent cosmic moment we call now. As we drift through this cosmic journey together, I hope these glimpses of the universe are expanding your horizons just as they do mine. If these stellar discoveries and cosmic wonders resonate with you, consider becoming part of our constellation by hitting that subscribe button and sharing this video with fellow stargazers. The universe may be infinite, but our time to explore it isn't. Your support fuels our mission to venture further into the unknown, whether through joining our Galactic membership for exclusive deep space content or sending a gravity-defying gift that helps us reach new astronomical heights. Remember, in the vastness of space, every connection matters. Thank you for being a bright spot in our cosmic community.